So it is a really big honor to be here, so thank you. I'm pretty excited to be here today to talk about scaling at Facebook. So I'm going to be talking both about a lot of the technical challenges we face and a lot of the sort of more people-centric issues of scaling, because Facebook is really about both these things. So we started at Facebook 4 years ago, and at the time we had 7 million users. That seemed like a really big number at the time. We've added a few people since. So actually when I started, the graph looked very similar to this, except there was a 7 on top instead of a 400. And in this whole time, it hasn't really let up, and it's showing no signs of it. So you can imagine this leads to a lot of technical challenges. These are some of the big numbers we deal with. Some of the ones I think are most interesting are doing 100 million queries a second to our cache layer. We have tens of billions of photos. So there's a massive amount of information, and all these are growing really fast. They're growing as new people log on to the site and new people sign up. They're also growing as existing users continue using the site. There's another thing that's also growing, which is so back in 2006, when we had 7 million users, every single one of those people was a US college student. And so they had largely the same interests. They all spoke English for the most part. In the middle of the night, they were mostly sleeping, so we could work on the site then. This is no longer true. We have users all around the world, users with all kinds of different backgrounds, people from different cultures, different ages, people who want really different things out of the site. And what this means to us at Facebook is that we have a lot more code to handle all these cases. Our product is a lot more complex, which means more code and more developers. And so in addition to the scaling problems around scaling systems and scaling servers, we also have a people scaling issue of this product gets more and more complex. This is something that's particularly important to us at Facebook because as an engineering team, we really value being able to move fast and being able to launch new products and being able to react to things. And so having a more complicated product works against that. And so that's something I'm going to be talking about today. Sort of how so I'm going to talk a little bit about why we value moving fast. And then I'm going to talk some about some of the specific technology we use to scale our servers and sort of the general principles we think about with that. And then I'm also going to be talking about some of the more web-centric, the front-end client time. So how do we make the site fast for users, which mostly has to do with what goes on in the browser and what goes on in the client code. And through all of this, I'm going to be talking about how we try to do this in a way that keeps our engineering team able to move fast. So if we look back at this growth chart, so there was nowhere along this growth where we could stop and say, oh, wow, we got through that one. Let's catch our breath and think about what we're going to do next. Every week we have our biggest day ever. So sort of in the most general sense, the way we deal with problems of scale is we've got to be able to deal with unexpected things very quickly. And that comes back to having a team that's able to deal with things quickly. Now, obviously, we know where this is going, and we can predict a lot of things. But you never catch everything. And unexpected things happen when you have your biggest day every week. There's a second reason why we like to move fast, which is that most of the products we're building are in a fairly unknown space. The hard part isn't always just building the thing. It's actually building the thing that people are going to use and people are going to like. And the only really good way to figure out what people are going to like is to try a lot of things. And the way you get to try a lot of things is you move fast. And so this is actually one of the numbers I'm most proud of at Facebook. We have about 1 million users per engineer. And this is due to our philosophy of having very small teams that are able to move quickly. So what do we do to move quickly? I guess to start, just talk about the world we live in. So with the website, we have a wonderful situation. We don't have a lot of external things. We don't have big partners waiting for a particular feature on one day. We don't have a big shrink wrap release we've got to be ready for. Very little externally is controlling what we do, except that the site can't go down, which is sort of one huge external problem, one huge external constraint that we can't really bend. So the way we deal with this is that we have a culture of making very frequent small changes. And so essentially when we're rolling out new products, we will change things a little bit at a time and very closely watch, measure everything and closely watch to make sure that things are not breaking. Even when we're doing a major system, if we're entirely replacing a big piece of infrastructure with another big piece of infrastructure, we'll actually pull them both up in parallel and first blast a lot of traffic at the new one that doesn't actually go to users and make sure it seems to behave the way we want it to. And then we'll very slowly dial a few users at a time from the old system to the new system and the whole time watch what's going on. And then if it doesn't work, which usually you have a few tries where it doesn't, you dial it back, figure out what went wrong, fix it, and try again. One of the things that's great about this that isn't obvious is that when you have, it makes you really good at dealing with problems that show up in production, because if you have a big bug that's affecting a lot of people, usually the vast majority of dealing with it is figuring out what went wrong. But if you only changed one thing at a time, it's really easy to figure out what went wrong. So it makes it really easy to deal with problems as they arise. So I'm going to switch gears and talk some about our server scaling. And so to understand the problems that we face in scaling our servers, a lot of them have to do with, as John mentioned, the fact that this is a very large amount of data that's very connected. It all depends on each other. And so to give an example of sort of the connectedness of the data, I'm going to go through the example of our Photos application. So how many of you have used our Photos application? A lot of people don't even think of Facebook as a Photos application or as a photo sharing site, but we're actually the biggest photo site on the web by far. We actually have been since the days when it was college students only. And we don't have a lot of features you might expect from a photo site. You probably wouldn't launch a photo site with the set of features that we have, but we're the biggest one in the world. And it's because of exactly one feature that dominates all the rest. Is in a Facebook photo, you can say who is in it. And so it turns out that by far the most interesting thing about a photo is not what its resolution is, not what it looks like, not how you cropped it, is who's in it. And that actually turns out to be true of almost everything in the world. What restaurant you're going to go to tonight is the one that your friends are going to, or maybe even the one your friends go to all the time and talk about. It's also true of people. So if you ask, who am I could say I'm 6 feet tall and I have blonde hair, and that doesn't actually tell you anything particularly meaningful. If I tell you I went to Caltech, I have 4-year-old twins, I'm training to run a marathon, that's actually something meaningful about who I am. And what that is are the things that I'm connected to in the world. And so we call this the social graph. This idea that the thing that's actually interesting about objects in the world is what they're connected to, rather than just their own properties. And we believe the reason that Facebook is such a rich experience for being able to communicate with people is that it actually sort of is built on top of this graph and recognizes this graph rather than ignoring it. This is also what makes scaling interesting. So because everything has to do with this interconnected graph, you can't just say, I'm going to take your data and if you live in Europe, you're going to be served out of the European data center and we'll put your data there and we'll put these people's data over here. Because you're not looking at your own data on the site, you're looking at all your friends' data. And everybody is friends with everybody else. And so you also can't make this assumption that, okay, we're just going to page in sort of the 1% of users who are on the site right now. You basically, the whole data set is with 1 or 2% of the users, you essentially have to pull in the entire data set to be interesting. So there's also a lot of data. If you think about what's on one of our pages, so this is my profile. The homepage is actually even more complicated because it has all the things my friends do. But each one of these things has a picture, it has a name, there's a name of the thing that the person interacted with, and most importantly, you actually have to check if the viewer is allowed to see all of these actors, and that depends on a non-trivial way in which these things are connected. So all of this has to be assembled in real time. This is easily hundreds or thousands of pieces of information per page. And all of this has to be pulled in real time to actually decide who's allowed to see this and what's going to be interesting to show to this user. The data also changes a lot. If you think about a lot of the things that are on the site, a lot of them really happen in real time. Somebody posts something and people comment on it and that makes a little conversation. And so this is changing a lot, and it actually needs to be fairly consistent. People often say to me, oh, it's not like you're building bank software, you don't really have to care about this stuff. But people do care about this stuff. And I would say that losing a picture of somebody's kid is just as bad as losing their money. And in terms of consistency, because this is a real-time conversation going on, you can't actually get these things misordered or drop messages or things. It quickly becomes unusable as a user. So specifically, we have to, if you post something, somebody needs to be able to read it no matter what data center they go to. And so in practice, how we do this is we do a write in a local data center, and then we mark that user as dirty, so that if they happen to bounce to a different data center in a different part of the world, then we know to redirect them. We also have to keep a consistent ordering of messages. We'll potentially let that be out of order for a little bit, but it needs to settle to being a consistent order. And we really try to have that. It's pretty important that these things show up consistently from data center to data center, because if you misorder a conversation, it actually is confusing to the user. So the other thing I wanted to mention, this is not at all novel, but I can't really give a talk about scaling about starting with this, is we have to spread things horizontally. So at Facebook, we have basically no choice of this. This data has to go on thousands of machines. But I'm going to quickly make the case why even at not that size, it really does make a lot of sense to scale things horizontally. And we see this again and again with applications in Facebook. Somebody will have something new, and they'll say, oh, yeah, I'll just throw it on one machine. It's not that many people are going to use it. And invariably, they're back fixing this thing and breaking it apart. So for example, I have a database with users, and it's running out of steam. And I say, OK, well, that's really an account and a profile. And those are different things. So I'll just split them apart. That's a lot of work, and you've gotten 2 times better, which at Facebook would buy you 6 months. Some other places maybe even less. So basically, as soon as you do this, you got to start doing it again, and the next one's harder. If instead you basically say, I'm running into trouble, I need to handle the case where 2 users are not on the same database, now I can spread it to n databases. And that's maybe a little bit more work, but that's the kind of thing that gets you ahead where you don't actually have to worry about this problem again for a long time, and you can worry about something else. So basically, our scaling situation on the back end is we have this very large connected data set. It's changing pretty fast and spread across thousands of machines, and we fan it in at real time. So every page we display, we have to fan in a huge amount of small objects over the network. So this is the system we use today to do this. So a request comes in and it hits a web server. This is a web server that's running PHP, and it takes essentially that's running a program to assemble the page. It pulls the data in from the back end. So it's pulling in a lot of data, doing some fairly simple calculations on what to show, and then displaying that as HTML. These machines are completely CPU bound. And in terms of scaling, not a big deal. They parallelize very nicely. So I'm not really going to say much more about that, although obviously the efficiency of these things is important because we have a lot of them. The next set of machines are Memcache. So this is where a lot of our scaling work to date has fallen, is in dealing with this layer, because this is the layer that basically serves up these 100 million objects a second to service all of these pages. So the first thing we need to do with Memcache is just make it really, really fast so it can handle lots of requests. And so this is something we put a lot of work into. It turns out that these machines are basically spending CPU in the kernel, pulling packets on and off the network. So we did a lot of work basically breaking up lots of locks so it can spread across cores, and being able to handle network across lots of cores, and being able to very efficiently pull packets on and off the network. The second thing is that basically all of the traffic flowing in and out of these things is a huge burden on the network. So a lot of the scaling ends up being in how you can get these packets moved across the network. And in particular, it's a question of burst packet rate. So essentially, we're not pushing a huge amount of throughput out of these machines. We're pushing a lot of packets, and those packets tend to come in bursts. So this is an example of one of the things that we've done. So you have I have a PHP program, asks for, say, 100 keys from 100 Memcache machines. And these Memcache servers are now really, really fast. They're running over a fast network. Within a few microseconds, they'll reply with a big chunk of data, and invariably we drop a packet. And so specifically, we would drop it in the buffer of the switch, the top of rack switch facing the PHP, the server running PHP. But basically, even if that buffer were infinitely large, we'd overrun another one. Essentially, we're pulling data in. There's really no network that we're not going to be able to overrun. And so the traditional way to deal with this is a timeout. If you have a default TCP timeout, that's way, way longer than we want to sit and wait in our data center. You can tune that really small, or you can use UDP and write it yourself. But there's a problem you always run into with doing retries in this situation, which is that the client can't tell the difference between a drop packet and a server that's slow. And by far the most likely reason a server is going to be slow is that it's overloaded. So what happens is that as soon as a server gets overloaded enough, it gets going along just fine, getting more and more traffic until it slows down to the point where it's missing the timeout window, and then it gets hammered with packets and it dies. And so instead of doing retries, so basically what this will lead is that whenever we got overloaded machines, they just fall over, and we'd have sort of turned small problems into big problems. So instead what we do is we keep a window of how many servers we can talk to at once. So this picture is doing 2 at a time. And so this is essentially a throttle. So rather than being a throttle about how much data I can pull per unit time over a connection, it's a throttle of how many machines can I talk to without overwhelming the network. And we scale this dynamically. So each PHP server just keeps a window of number of open connections it can have at a time, and it scales that up and down depending on whether it's successful. There's been a huge improvement both in making failures not cause as much trouble, and it actually about doubled the speed of the system. So we were able to, because we weren't dealing with timeouts, we made timeouts very rare, and we actually made the whole system considerably faster. So the other piece to scale is the database. So it's actually a little bit of a misnomer to call this a database. We call it a database because it's running MySQL, and that's a database. But its role in the system is really as persistent storage. And this is something people talk about a lot. Do you need joins and indexes on your database? And you don't for 1,000th of your data. So we don't really use any of the advanced features of MySQL. We're still doing joins and indexes. But sort of in this whole system, you can think of this whole system as a database system where the web servers are doing essentially joining, and the Memcache is holding lots of indexes. But this database down here is basically trying to get bits safely on and off disk and efficiently. So here, our issues for scaling are really about how much data we can get on this machine in a way that we can actually still read it at a reasonable rate. So the work here tends to be around clustering data well on disk and sort of getting the right things in memory. And that actually ends up being a little bit tricky because our data has a lot of temporal locality. Recent data is much hotter than old data, but it actually varies pretty widely between application. It varies pretty widely between people. So something on my profile, the oldest thing on the front page of my profile might be 4 or 6 months old. Somebody with 1,000 friends whose birthday it is, it might be an hour old. So essentially getting things lined up on a cluster on disk in ways that we're actually going to pull the right information into memory becomes really the challenge with the databases. And as I was saying, it really is a misnomer to call that a database. So this is actually how we try to think of these layers as a web server, distributed index, and persistent storage. And so the things we're working on now are trying to build systems that actually fit in these layers better than Memcache and MySQL. And so one of the problems we run into is we increasingly want to do products that ask more interesting questions of the graph, things that aren't easy to do with a Memcache data model. So for example, if I want to ask which of my friends plays Farmville, that's the sort of question we want to ask all the time. And there's no really easy way to do that with Memcache. If you sort of have a naive solution, you basically, if you're doing all the processing client side, you either have to pull in all the applications that all my friends use, which is a lot of data, or all the people that use Farmville, which is an even a bigger amount of data. And so the way you really want to do that calculation is send my list of friends to the server that contains the list of people who play Farmville and run an intersection there. Memcache doesn't let you do that. MySQL would let you do that, but it's too slow to be able to use for any real application. And so we're sort of stuck here between this Memcache model, which is super fast, is great, but it is really too, it doesn't let you do a lot of the things you want to do. So you end up either doing things that are too expensive, or you write a lot of complicated code to work around it. On the other hand, the database is anything you'd ever want, but it's too slow to actually use it. So what we're building now are systems to think of the world as a graph, sort of a middle ground between this. Almost all of the things we do are very well expressed by this, which is essentially an adjacency list representation of a graph. So instead of having the key value model of you have a key mapping to an opaque bunch of bits, you have a key mapping to a set of objects. And with that set, you can append and remove objects, which is really good for things like people who play Farmville, where you have a very large set that gets lots of incremental changes. And most importantly, you can run intersects against it, which is the primitive we need for doing most of our calculation. And so this is what we're building now and how we're thinking about our new applications that we're building. Actually, before I talk about client performance, there's one other subject I wanted to talk about, which is failures. So one of the things that we deal with when you're running with thousands of machines is dealing with lots of things that go wrong. And so the simple answer is that if you spread things horizontally, then you've got a pretty good case for dealing with failures. Any particular machine going down doesn't, it only represents a small percentage of the site, so it's not a big deal. But the thing that's really important is to make sure that when one machine goes down, you don't have essentially feedback loops where other machines start to go crazy and they go down too. So the retrying is one example. If a machine goes down and the default behavior is everybody just to pound it with packets, then that starts causing secondary issues. The other thing we see a lot is that almost all of the real failures are not because of hardware. Almost all of the real failures are because of software. And so if you're looking at single points of failure in the system, one massive single point of failure is all these systems run exactly the same software. And so we've seen this again and again. So for example, back in the old days with photos, we had at one point 20 squid machines sitting in front of our photos filer. And we knew that the filer couldn't nearly handle the request rate for the I/O. And that if we lost this cache, it would take a day or two to build it back up. I thought, this is fine. We've got 20 machines here. They're completely independent. We're not going to do anything crazy. If one of them goes down, that can fall back to the filer, and that's fine. So we start up these 20 machines within about 10 minutes of each other. And it turned out our load balancing was quite good because they leaked memory at almost exactly the same rate. And a week later, they all fell over within a half an hour of each other. And we had to build the whole thing from the filer. So, we see this again and again. And, and when our site does go down, it's most often because we pushed a change that doesn't work, and we push it everywhere really fast. So this is, again, to get back to the point about doing things incrementally. When we're changing software, it's really important to run it on a very small number of machines and very slowly roll it out to a wider number of machines. And there's a handful of things you can't do for that, things like configuration if everybody has to agree on which machines are in a set. And those need to be handled very carefully. But almost all software upgrades you can do in a very slow roll. And so when I say we want to move fast, we want to move fast in terms of getting changes out, but then when it's actually time to apply it, you get a lot of value out of very gradually rolling it out. So the next thing I want to talk about is performance of the website. So the thing about performance on the website, the time the user sees, not everybody realizes this, actually has not a lot to do with what happens on the server in the data center. The time a user is waiting for a page is almost completely dominated by time on the network and time in the browser, pulling in all the little pieces of things it needs to show the page. And so it really ends up being dominated by how many images, how many JavaScript and CSS files are there, how large are these files, how well are they packaged, how well is the browser able to pull these things down in parallel. And so one of the things that happens with this is as your product gets more complicated, these things get a lot slower. So when I showed the picture of us spreading across the world and more people are using Facebook and we're adding more and more features, this makes our product get a lot slower. This also doesn't play well with our idea of moving fast, and we're going to launch features really fast. That means we're adding code really fast. And so, we used to joke that, yeah, our team moves fast, but our site doesn't. And so last year, we decided to do something about it. And we cut the speed of the site in half. And so starting in June, we were about 5 seconds for a page load. And by December, we got it down to 2.5 seconds. And if you think about this amount of time, that 2.5 seconds times several billion hits a day is actually hundreds of years of people's time every day. So we're actually saving several lives a day by making Facebook fast. And the second thing we wanted to do is actually try to set up a system so that we could continue having it be fast while we move quickly as a team. So that's so in addition to making the site fast, we wanted to try to get to a more sustainable place where we can continue to build new features and not have it always slow down our site. So before I talk about the specific things we did, I want to talk a little bit about what makes this stuff slow. So a lot of people have this idea that the performance engineering is, sort of this black art where you've got to have this deep knowledge of systems and algorithms, and you make very careful trade-offs, and you play crazy tricks. And a lot of real performance engineering is that. But the reason why most things are slow is just because there's too much stuff. There's too much code, and there's stuff that basically looks like bugs. There's a very complicated system. People change it. It has unintended consequences, and sometimes those unintended consequences make things slower. So to put more simply, and because you have, because these things are like bugs, it's the same thing that you can't expect to write a new piece of code and not have bugs. You can't write a new piece of code and expect it not to have performance problems. So what we've found is that new code is slow and more code is slow, which is, again, a very big problem for us because we're very good at generating lots of new code. So what do we do? The first thing we did is essentially take this new code and age it. So just go through and say all of these problems that we've introduced, we're actually going to, instead of spending time generating these things, we're going to spend time just going through and fixing them, putting in the hard work of track down what are all these subtle things that are making something go slower. This is really just a lot of hard work. And it's something that we're thinking about moving forward is that whenever you're generating new code, there's a certain amount of time you spend generating, and you might need to spend a certain amount of time aging it too to make it work well. And then we also did 2 big systems projects to try to sort of tackle this more systematically. The first is called Big Pipe. So if you think about a Facebook page, it actually is a bunch of different regions of the page that are fairly independent, sort of representing the different features on the page. Each one of these has a pipeline it needs to, or has a series of steps it needs to go through to show up at the user. The server needs to gather data. The server needs to turn that into HTML. That HTML is sent back to the browser. The browser needs to pull in all of the external dependencies, and then the browser needs to actually render the thing. And so instead of taking sort of all the things on the page and going through each of these steps for each chunk of these one at a time, we basically say we're going to split these apart and we're going to run a pipeline. And so what that means is that when the request arrives at the server, as soon as we know that we don't need to redirect a page, we can send back a header that tells the browser what resources to start downloading. And then as soon as each section of the page finishes generating, we send that back to the browser, and the browser can start rendering it. And so we get 2 things out of this. One is that the stuff the user really cares about at the top of the page pops up before we've spent all of the time doing the rest of the stuff. And the second thing is we get enormously more parallelism by running the different stages of the page in parallel. So we get the browser and the server time overlapped. Second thing we did is we wrote a really small JavaScript library called Primer. And what Primer does is basically it does the bare minimum of things you need to make a page feel like it's interactive when it loads. So these are very, very simple primitives. The most important of which is that if you ask for functionality that isn't loaded yet, it can load it in, which we call the bootloader. And so this allows us to keep the core of it very, very small. And so both BigPipe and Primer have the same property, which is they separate the world into basically a fast path and a slow path. And it defaults things into the slow path. So this, again, isn't really a novel idea in computer science, but it's something that's pretty unusual in web frameworks. For the most part, when you're writing web code, you say my new feature.js, I throw that in, include in kitchensink.js, and it goes on every page and it slows things down. And that's certainly how things used to work at Facebook. But now we get it separated. So as an example, say I have an idea for a crazy new feature. And it's called poke. And I don't really know exactly what it is or what it does or why it's there, but I want to give it a try. So I write my code for this, and I put it on the page, and I stick it at the bottom of the page, and it isn't going to affect anything else that's going on. So while the top of the page is still, so by the time any server is worrying about generating my poke feature, the user has long since seen the part of the page they care about. This is great for the site because crazy new features people are trying out don't slow it on the site. It's great for me because I don't have to go talk to somebody to get approval to put my feature in. I don't have to run a bunch of tests. I don't have to do a bunch of hard work if it turns out that this isn't useful. But say it does turn out to be useful. Everybody loves it. Everybody's poking everybody else. And we're going to move this right up to the top of the home page. So this is the point at which we actually do the hard work of the real performance engineering, of making lots of trade-offs, playing crazy tricks if we have to, really thinking about how can we support this with, do we have to add a feature to the core library or not? But we're only doing this exactly where we need to, and everything else can keep going. The second thing we come to, once we decide that this is up at the top, once this is important, now we have to measure it. And so in terms of performance measurement tools, we've actually found there's really sort of two classes of tools, and people often conflate the two. There's the kind of tool that, given something is slow, how do I figure out exactly what's going on so I can make it not slow? Essentially a diagnostic tool. And this is very analogous to a debugger. The second kind of tool is just something that tells you that something is wrong. And the reason I make this distinction is people often conflate the two, because if you essentially try to use the debugger to tell you if something is wrong, it's really hard. So you can take these tools, you can take a profile. So we have a tool that profiles every single function in our PHP code, can tell you exactly how long it took every hour off real production servers. Charting this data is not actually very interesting because people move things around, they rename things. Stuff is changing all the time, and finding things that are actually slower versus just things that have changed names is really hard because the granularity is so low. So you can take the flip side and say, okay, well, the thing I actually care about is that my site is fast. I care how long do users wait on average, or maybe at some percentile, to see their page. So you can do that, and what happens is, to say I have my new poke feature, and I made it super poke, and it takes a little longer to generate, but it's really great. And you come to me and say, the site's 1% slower now because you made that change. Do you think I'm going to care about that? I'm bringing pokes to the world. And so what you really want to do is come to me and say, your poke feature just got 50% slower. And then it's like, oh my God, people aren't going to poke as much. So I better go fix that. I better go make it fast. And so the thing is that you need to have essentially the granularity of the alerting tools basically match to the granularity of what one person does and what one person works on. Because at the end of the day, it's going to be one person who goes and fixes this thing, and they're going to do it because they care about it. So I'm going to, I guess, say a couple more things about sort of engineering culture and how you get things together, how you get people to do things like make the site fast. So this is sort of a general class of problems of things that are globally important but aren't necessarily important to any particular team. And so, as I said, we have this culture of lots of small teams going off and doing, trying to very quickly get done what they need to get done for their feature. And so you can often have these problems like site speed that build up over time. So there's two basic principles. One is that if anybody's going to do anything, they got to care about it. It's obvious, but very important. The second one is that if somebody is responsible for something, they actually have to have control over it. And that's something that it sounds pretty obvious, but people violate it all the time. A classic example is if there's somebody who's deploying code that somebody else wrote. And this person who has to deploy the code feels responsible. Am I going to break this thing I'm deploying the code to? But if they do, it's because of a bug that somebody else wrote. They're not able to fix it. All they can do is call this person up. And so what does that person do? Basically, their only course of action is to say, no, I don't want to push that code. I don't know if it's going to have bugs. And so essentially, when you separate control and responsibility, you create people whose only way to handle their responsibility is to say no to things. So you get people who just slow everything down. And so sort of applying this to how we do performance engineering, we sort of have, we've tried a wide variety of models. One of them is you have 3 or 4 people and say, like, it's your job to make the site fast. And this is great in terms of people getting things done that they care about, because those people will care about that. They're going to wake up in the morning thinking about how am I going to make the site fast. It completely fails the control and responsibility test, though, that these people are now responsible for this, and most of what changes is because of all the application code being written, all of the product changes. And so these people are put in a bad position of being gatekeepers or feeling like they have to fix everybody in the world's bugs. They're not happy. You can distribute it out and say, okay, every product team is responsible for what its performance is. And this works great in terms of the people who are responsible for having control over it, but it's not great in terms of people caring about it. There will be a few people who care about it, but even the ones who do are going to have a lot of other competing priorities. So we tried to go with kind of a hybrid model, which is we have a few people who are a centralized team. And so their job is not just to go fix everything that needs to be fixed to make the site fast. Their job is to build tools, to do analysis, to understand the problem, and then to work with the product teams. And then on each product team, we get one person on that team to be a point person. And so the idea is that this person is a representative for performance on that team. But they're still part of that team, so they still understand how the code works, they know the people. If something needs to change, they're able to do it. If something does change, they know what happens. But then they're a single point of contact for the central team, so that when we have wider things that need to happen, the centralized team can identify those things and they can get them done across the system. And we've actually been much more successful with this model than any we've used before. And we have actually, so last year we did a big push to make the site twice as fast, and we've made it even faster this year, and things are looking a lot better for making this sort of thing sustainable. So to kind of recap, the things that if you didn't take any lesson away from this is the stuff I think is actually really important, is to go back to the server scaling. You want to federate everything. Basically, the first answer to any scaling problem should be split something into lots of pieces, and not 2 or 3 pieces, but n pieces. Try to make sure you keep your failures contained. Trying to be too fancy about your error handling usually ends up when you're in your most vulnerable, you're running code that has never run before, and will often cause more trouble than you want. If you do a good job of federating things, you should be able to allow just something to go down and replace it in a reasonable amount of time, and it's not a big deal. You should dark lodge anything. Running at scale is a use case that's hard to test, but you need to put the effort in to test it, or dial it up really slowly and watch. And then in terms of site speed, it's really about just recognizing that new code is slow, and so you need to either put the effort in to age the code, or have a place where people can put new code that doesn't break the things you really care about. And then most importantly, you shouldn't have anybody in your organization whose job it is to say no to things. And so, with that, I guess have some time for questions. So. Yeah. I guess you can.
Yeah, I guess I was really impressed with this social organization that you talk about. I mean, you're saying you've come up with this notion that one person should not have responsibility, no control. Where did that come out of? I mean, this doesn't sound like a bunch of engineers to me.
Yeah, I think it. Yeah, I think it did come out of our engineering culture. It's something we internally spend a lot of time talking about and worrying about.
Yeah, obviously.
And
it works.
What's that?
And it works, right?
Yeah, it works great. It's almost any conflict you can point out. Sort of the classic one is between operations and development, but almost any one of these you can track down to somebody is frustrated because they feel responsible for something they can't control.
Okay. Yeah, I mean, that, like I said, I'm just blown away because most of the time, people want to talk about the technical issues rather than the social ones, and yet this is really this is something social that affects the technical. I'm very impressed.
Yeah. Well, thanks.
I also thought that was pretty cool, although I don't know that this audience is the right audience that needs to hear that, right? It's directors and vice presidents and everybody else that decides these things. But I had a technical question, which was,
yes.
You talked about the TCP incast problem.
Yes.
And you're essentially handling it at the application level in terms of watching, what comes back over the socket, something like that.
Yeah.
And you also talked about packet handling, trying to make that really fast. I assume you're using Linux for the operating system.
Yeah,
you never
correct.
said that. Do you make custom changes? Do you feed them back upstream? How do you?
Yeah, so we made a lot of changes in the network layer in Linux, specifically for the Memcache servers. So on the server side, that was essentially we changed the driver model to pull the sockets and be able to pull for data off the sockets from all the cores. We didn't send it back upstream because it was really hacky and it had possibility for misordering packets, which we don't care about and everybody else in the world probably does. And it actually is much less important on modern hardware. So I believe that the boards we're buying now actually, and with the modern kernel, you don't actually need to make that change to get it spread. Because the problem we would see is that you'd essentially have one core pegged in I/O and the rest of the core is idle. Did you have a?
Well, yeah, so you don't have to maintain this anymore, in other words? Because it's tough to keep holding that, especially the way Linux moves, right?
Yeah, so I believe we still run a lot of machines with a custom kernel for this. And I think we're basically in the business of we're always going to have some things modified. So at this point, we build our own kernel. But definitely try to stay on trunk as much as possible.
Okay. There's some new standards coming out of IETF in terms of data center bridging and data center networks that might help solve some of these problems. So, I mean, your larger point about you're always going to have something unique to you that is
but yeah,
there are other people facing that problem too.
Yeah, great, thanks.
So if I understood you correctly, your social graph essentially needs to stay entirely in memory, is that right?
That is correct.
So should I infer that basically all of your data pretty much has to stay in memory?
No. So there's essentially two classes of data. We have data that's the graph data that's basically time independent, and that basically all has to stay in memory. It's actually in memory many times because we have a bunch of, basically in every data center it has to be in memory, and it's often in memory in sort of in various index forms. There's also data like messages that get paged out, that basically age out nicely, and so those end up on disk somewhere. Basically on disk on a database, hopefully not actually getting paged in very often. We're increasingly looking at using Flash for a lot of the stuff that's kind of in the middle ground. So that would be just sort of, either less current, second page sort of data, or graph data that's not queried as aggressively at runtime and we can deal with a slightly lower rate of IOPS. And then the final kind of data we have is video and photo data, and that all ends up on disk. So that basically goes on SATA disk, and we've done a lot of work there to basically, because the data is essentially uncacheable. It's petabytes of data. So we've done a lot of work to get sort of all of the directory information very, very small so we can keep an index in memory. And then when we essentially have an index of like a photo ID to a file and a length and an offset, and be able to hit that with exactly one disk I/O.
Okay, thanks.
Thanks.
You made the decision to take your data and split it into multiple databases, and it sounded like that when a request comes in for a particular item of data, the server is the one that decides where it has to go to get it? potentially redirecting the client somewhere else. Is that correct?
Yeah. So the web server basically has the map of where all the data is, both at the database layer and the cache layer.
I was curious if you had experimented with pushing that out more towards the client by embedding that information in the HTML that initially goes out to the client so that it goes to the correct server to begin with. Mm-hmm. Is that something you've considered doing or experimented with?
So we can't do it at the data layer because basically all of our data is subject to complicated privacy rules that we can't push out to the client. One of the things we haven't done a lot of that we probably could get some pretty big efficiency wins are right now basically clients go to whatever data center is closest, they hit a load balancer, they land on a random web server. Something we've talked about a lot but haven't actually done a lot of work on is figuring out if there's ways of keeping particular users clustered in areas where they would share a lot of the same data to be more effective in the caching. But as it stands right now, we basically send a user anywhere, and most of the data set is just cached almost everywhere.
Thanks for a very interesting talk.
Thanks.
So you said that new code is slow, which is true. Could you speak a little bit more about how you age that code, how you find the performance problems before rolling them out?
Well, so we often don't find it before rolling it out. Mm-hmm. So we've actually kind of given up on that. You can catch the really bad ones before they go out. So a year ago, we were all about, like, okay, we're going to build a bunch of tools that are going to catch everything so we never have a problem, and it didn't work. You catch the ones where somebody made this thing twice as slow and the whole site goes down. But yeah, you really just it's just essentially you launch the code, you see that the whole thing is slower, and you just got to pick through. And so we have the tool we use most often is we have a profiler for PHP that gives us a PHP level profile of all the inclusive and exclusive time in all the functions. And we actually sampled data from production. Because another one of the things we found is that our workload is so varied in terms of what pages people view, things behave very differently for different kinds of users, that synthetic tests catch the big ones, but they don't catch the subtle things. And so we really just taking massive amounts of data from our actual servers is far more useful than anything else. And so, yeah, it's just a matter of going through and finding what are the bottlenecks, what are the things that changed week over week. One of the things we've tried to do is, and again, that's hard because lots of code changing, you could have a function, you move a couple things around and something that was expensive used to live in one function and now it gets called the first time from something else. So one of the things we're trying to do is build tools that essentially like tag groups of functions so that you can essentially quickly look at this class of things got worse or better, or this class of things, either whether that's a product sort of vertical class of things or a horizontal class of things like the rendering layer got worse. But yeah, it's really just the hard work of looking at profiles. And I guess there's also data, because everything is so data-centric, we do a lot of profiling of what objects are we fetching from what pages, what queries are we running most often, and trying to look at trends of those.
Great, thank you.
How important are the issues of data consistency? So at least a little while ago, it was possible to play with the UI to get comments to appear out of order and do little things like that. Is that much of an issue these days?
Yeah, there definitely are a lot of cases where things can end up inconsistent and misordered, and that's something we care a lot about. It's something we're actually putting significant amount of work into replacing. One of the issues you run into with is also with this Memcache data model, where it's just a key and a value, and your only operations are to set the value or delete it. Is pretty awkward for dealing with consistency through a lot of databases. So we're putting a huge amount of work into basically redoing our system so that we can. One thing I didn't mention is we're moving to more sort of graph servers instead of Memcache servers. That also is a write-through model that's able to, and something like I want to append this object to this list is much easier to deal with in a distributed sense than, here's a whole new object, good luck comparing it to the old one. And so, internally we spend a pretty significant amount of our time dealing with bugs in the current system and trying to get the new one to work, because we really don't want a system where things can misorder or things that move around on you as a user are extremely frustrating. Thanks.
So you talked a little bit about rolling features out slowly and kind of taking the wait and see model to deal with failures. And yet the example you gave was a memory leak where it took a week for all your servers to fall over.
Yeah.
And so this sort of leads to the obvious question of how on earth do you know how long to wait to see that things are okay?
Yeah, that's a good question. In fact, that's exactly what bites us with this model. It mostly depends on how bad it's going to be if it's a problem. So, for example, when we roll out Memcache servers, that has a very, very big downside because if we invalidated our whole cache, if we had a bug and all of our cache servers died, it would take us a long time to rebuild it. So those we can easily spend a month rolling out a change to that. So it'll be a server for a few days, and then 10 servers for a few days, and then 1,000. In terms of our web code, where it's application code and problems are usually quickly apparent, then that's more on the order of a few hours. Databases also, we've spent months rolling out database releases because that's sort of the worst thing you can do is to corrupt the data. And so yeah, I guess it just varies entirely on how bad it's going to be if we screw it up.
Thanks.
So you've talked a lot about the short time aspects of serving data to customers quickly and make it optimizing the retrieval. I was wondering how you deal with long-term data storage, because as you say, Facebook is the biggest photo sharing website on the web. You've been going at this growth rate for about half a decade now. It's getting huge. Where do you see yourself 10 years down the line? Because you're going to have a data set. If you get all the photos in the world and the rate at which people produce photos is increasing, then you're going to have a massive long-term storage problem at some point, and you will either have to, well, I guess, delete some data or find a really efficient way of compressing it, or make some decision of how you deal with this huge volume. You can't, you can just keep buying hard disks, but at some point there will be a scaling issue there, I suppose. Have you thought about that and what are your current solutions?
Yeah, so currently we just buy lots of servers with lots of cheap SATA drives. And one of the interesting things about the scaling is we've been around for 5 years, but probably more than half the data is from this year. And so it's actually the new data coming in is always as big a problem as the archival data. And so in terms of, disk drive manufacturers have been very helpful here. They keep getting bigger. So we don't get increases in IOPS from the hardware, but we get increases of size. So that's good for us. We're not ever planning to delete data. And again, because this going back and deleting the old data, there's so many fewer people 5 years ago that actually deleting the 5-year-old data just doesn't actually give us very much gain in terms of getting space. In terms of one of the things we're spending a lot of time with our structured data is with our databases trying to get a model that does a better job. Right now we basically run a database and we run batch jobs that dump out the old data and stick it on some machine that's sitting in front of a ton of SATA drives. And so what we're trying to do now is get more of a model where we can just age out the data nicely in place and basically have the hot data in memory, the general working set in Flash, and then push the rest out to SATA drive. And that data set isn't particularly big compared to SATA drives. It's really in terms of raw storage space, it's really only the photos and the videos that get really huge.
Right. So do you have the same degree of replication for data independent of its age then?
So the same what?
Degree of replication on hard disk storage, because presumably you do replicate it.
Yeah, I believe we're still running the same level of replication for everything. Right now for almost everything it's 3-way replication, and anything that's structured data is then backed up any number of times. And that's another way we possibly could dial that down in the future if it gets really massive.
Okay, thank you.
Thanks.
Hi, something I heard first from Mike Jones, I don't know if Mike's here, was that when you're on the exponential growth curve, what happened in the past doesn't matter. And looking at your chart with the exponential growth curve of users, I can see that you're on that. One thing that I see is that although I think you're going to hit a wall, at some point you're going to be fewer users joining, but each user is going to have more and more data.
Yeah.
So that's going to shift. I think it's going to have to shift the way you look at your problem. And the other thing that corollary to what Mike told me was the system that you have today isn't the system you're going to need in a year. And it seems like from an engineering perspective, you're taking a very incremental approach, adding new features and fixing small things. And I was wondering if you have taken on yet the philosophy or thought about taking on the philosophy of saying, we got to rewrite the whole system every year, because next year it's going to be a completely different system and a completely different problem.
Yeah, so that is something we, one thing about the incremental changes is it's very easy to have rewritten the whole system in a year. So while we're running, Memcache is the same thing we were running 5 years ago. That's, very few lines of code in that thing are at all what they were. It's the same protocol on the wire. Actually, not even that's the same. So no, it's. But yeah, we are undertaking a lot of longer term things now because we know this is going to continue. So one of the things we're doing is essentially trying to replace our whole cache layer with this much more with a much more natural data model that fits our application. Another big one we did, I didn't talk about this because it's not really so much a scaling issue, but we wrote a compiler from PHP to C++. And so that was something that basically one guy thought he could do this and started a year and a half ago, or maybe 2 years ago now. And over the course of a year built this thing. So we do have a lot of these longer term projects, and that's definitely important. But even when we're building the long term, I guess the other big long term project we work on is essentially we're rewriting the way that we handle replication around between data centers and around the world. And but even when you do this, we try to take the incremental approach of really decompose this into these are having a completely different way of shipping data around the world involves a variety of different pieces, and we're going to try to get each one of them tested independently and rolled out. So even if we are rewriting it over the course of a year, we're never going to have the thing where, okay, today we're flipping the switch from old to new and, good luck. So we always break things down into those kind of pieces, at least whenever we possibly can.
Hi, I have a couple of questions. One on the client performance you mentioned. Have you considered rendering picture data in a different scaled down resolution, depending on the client bandwidth capabilities?
Yeah,
storing or rendering.
Yeah, that's a possibility. Although actually, most of the images we send are thumbnails that are also very scaled down, so you don't have a lot more you can go there. We had. We potentially could, one of the things along those lines we thought about is essentially strip down the site to just not show profile pictures if you're on a really slow connection. In fact, we had the light site was sort of a try at this to see if it was actually useful to people and they liked it. So it's something we're not currently doing a lot of, but it definitely is an area that we're interested in exploring in the future.
Okay. The other one is on the failure. How do you handle SATA disk failures? Are there any plans towards going to a centralized storage system? Because doing all this application with this much scale is going to take so much computing power and efficiency. It's going to be a lot of overhead doing all the application of all this data storing in this SATA drives.
Sorry, I don't understand. What was the?
Do you have any plans towards moving towards centralized storage system model where you have central storage handling all this application capabilities and not the servers, keep the servers out of this?
Not right now. We've traditionally had better luck running sort of lots of small nodes with direct storage. It's again just because it has a really nice scaling property, and that actually turns out to be really cost effective for us to just buy lots and lots of cheap machines with sort of 10 or 12 drives, and that's so no, we don't have plans. We potentially could move to a model where we have a larger set of disks with sort of a few machines in front of it, but we just haven't gone down that path. That's our current model. Sort of all of our administrative processes, sort of everything we do is based around this idea of you sort of have a single machine that contains storage with it.
Okay, thanks.
Is PHP the right language for building web applications of the scale of Facebook? And if you could start from scratch and choose any language, what would be the right one? Or for that matter, is there a right one today?
Well, PHP is a fantastic language for writing web applications. It's not a great language for running web applications. And so that's why we wrote a compiler. So I guess is there a right answer is, well, you can do, as long as you can write a compiler, you don't have to answer that question. But yeah, I still think PHP is the right way for doing fast feature development. It's been enormously useful for us to be able to turn out features really fast, and you can do that really quickly and easily with PHP. There are a lot of people like Python. You can debate whether that's going to be a cleaner language for doing this, but I think sort of an interpreted language is actually the right level of abstraction. And so I think that it was the right thing for us to start with an interpreted language, be able to develop our product very quickly, and now we have the luxury of being able to go back in and make things faster where we need to, or in our case, write a compiler, or just chip off parts of the back of the PHP and try to rewrite those in faster languages.
I have one more question about this in-memory large graph you mentioned. So if you pack all your core data structure in this graph, so how it is related to data cached in Memcache?
So Memcache basically stores a representation of the graph, and it is sort of in the simplest form an ID so if you think of a graph as a list of edges, it is the ID for one end of essentially has two IDs and a type of connection, and so we essentially keep a cache of for my ID and the type of connection, all of the IDs I'm connected to in that way. And so the way we do it right now is that's just one opaque blob in Memcache, and what we're looking to do is change it to a model where you essentially can operate on each of those ID2s independently. But right now we basically just keep it all in Memcache, and so if I want to ask the question of, are you and I friends, I can pull a value out of Memcache, which is all of the people I'm friends with. I can also pull a value that's all the people you're friends with, and I can then, in the client, intersect those if I want to know if we have mutual friends. So that's the way we do it now. We play for various things. When these sets get really big, this obviously doesn't work, so right now we just basically play crazy tricks with sort of caching recent ones or caching important ones, or trying to be clever about how often we invalidate it if it's changing quickly. But we're trying to move to a model where our data is essentially stored natively in a graph format that handles these things easily.
So do you have an idea, so what is the size of this graph?
What is the size of the graph? I think we're in the tens of terabytes. It might be bigger than that now. It probably depends what you call the graph and what you call sort of other data. It's, certainly billions of connections, so you get many, many billions of friend connections.
So basically you split this graph into a lot of machines.
Yeah, so spread across several thousand cache machines. I guess actually we have 400 million users, and each of them has 130 friends on average. So that will give you the number of friends, and I think the number of objects is sort of on the same order, the number of non-human things you're connected to.
Okay, thank you.
Thanks.
Have you considered, or is there any plans for doing a reverse search based on uploading a JPEG and finding the person?
Oh, you mean I could upload a JPEG and Facebook would tell me who that is? I haven't thought about that one. I don't know if users would like that. But,
Any final questions? Well, thank you very much, Bobby.
Thanks a lot.